For most of human history, we believed the stars were stable, fixed, unchanging, reliable points of light that would outlive civilizations. That belief is starting to crack. In the last decade, several nearby stars have dimmed, flared, or behaved in ways our models didn't predict. Not over millions of years recently, and the more closely we observe them, the less stable they appear. Let's start with a star you already know, Betelgeuse, the red shoulder of Orion. A supergiant so massive that if you placed it where our sun is, it would swallow Mercury, Venus, Earth, Mars, and stretch toward Jupiter. For centuries it burned steadily. Then in late 2019 it dimmed, not gradually, not over thousands of years. In weeks, it lost more than 35% of its brightness. Astronomers were stunned. Betelgeuse is expected to explode one day. It's near the end of its life, but not like this. The dimming was too fast, too dramatic. Was it about to go supernova? If it had exploded, we would have seen it in daylight. A second sun in the sky. Instead, after months of observation, scientists found the cause. Betelgeuse had ejected a massive cloud of superheated gas. That material cooled. It formed dust. And that dust drifted between us and the star, blocking its light. Betelgeuse wasn't dying. It was shedding. That event forced astronomers to confront something uncomfortable. Massive stars are more unstable than we once believed. They don't simply burn fuel in a steady way. They convulse, they eject material, they reshape the space around them, and Betelgeuse wasn't alone. A few years earlier, astronomers discovered Tabby's star. Unlike Betelgeuse, it didn't dim once. It dimmed randomly, sometimes losing up to 20% of its brightness. No clean pattern, no predictable orbit. Planets don't block that much light. Dust clouds don't behave that chaotically. For a short time, scientists even considered whether something artificial could be responsible. That idea faded quickly. But the fact that it was even considered shows how unusual the data looked. The most likely explanation now involves massive clouds of debris, fragments from collisions, disrupted bodies, or unstable material orbiting the star. Still not fully understood, then came another case. A young star dimming by nearly 80%. 80%. For almost a full day, most of its light was blocked. Not a planet, not a simple eclipse. Likely a massive disk of debris or fragmented material. But again, the behavior didn't fit clean expectations, and here's where the pattern becomes clearer. This isn't about one star behaving badly. It's about the fact that stars are far more dynamic than our simplified diagrams ever suggested. Stars are not steady bulbs. They are unstable spheres of plasma. Their surfaces churn with convection currents larger than continents. Their magnetic fields twist and snap, releasing enormous flares. Their outer layers can be expelled into space without warning, even small stars, especially small stars. Red dwarfs were once considered calm and long-lived. We now know they are among the most violent stars in the galaxy. Proxima Centauri, the closest star to our sun, released a superflare in 2019. For a few seconds, it became thousands of times brighter in ultraviolet light. If an Earth-like planet orbited close to that star, its atmosphere could be stripped away, sterilized. And this is not rare behavior. Most red dwarfs flare regularly. Many planets in their habitable zones may face constant radiation storms. This changes how we think about life in the galaxy. For years, astronomers assumed that red dwarfs were promising homes for habitable planets because they are long-lived. Now we know those planets may endure constant stellar violence. But instability isn't limited to distant stars. Now bring it closer, our sun. It feels stable. It rises every morning. It warms the Earth. It appears constant. But in 1859, it unleashed the Carrington Event, a massive solar flare followed by a coronal mass ejection. Charged particles slammed into Earth, telegraph systems failed, equipment sparked. Some operators were shocked by electrical surges. That was before satellites, before global power grids, before digital civilization. If a similar event hit today, it would cripple modern infrastructure. Satellites destroyed. Power grids collapsed. Communications disrupted worldwide. Estimates suggest recovery could take years. And in 2012, a storm of similar strength narrowly missed Earth. By 9 days, we were lucky. Solar physicists now monitor the sun constantly, because we know it is not permanently calm. It cycles through periods of higher and lower activity. Sunspots increase, magnetic complexity rises, flares become more common. So what's really happening? Are stars becoming unstable? Or are we finally seeing what was always there? Here's the honest answer. We now have better tools. Kepler, TESS, James Webb ground-based arrays scanning the sky every night. For the first time in human history, we monitor thousands of stars continuously. We measure tiny changes in brightness. We track flare activity in real time. We map stellar surfaces indirectly through light variations. And we're discovering that variability is normal. Stellar surfaces churn. Magnetic loops snap. Plasma erupts. Mass is thrown into space. Radiation fluctuates. Stars are not quiet. They are engines. And sometimes engines misfire. But one case still pushes the boundary of what we understand. Przybylski's star, about 370 light-years away. When astronomers analyzed its spectrum, they detected signatures of extremely heavy elements, including radioactive elements that decay quickly. Elements that should not remain detectable for long periods, yet they appear present. One explanation suggests unusual nuclear processes in the star's outer layers. Another suggests contamination from a nearby neutron star or stellar remnant. The truth is, we don't fully know. And that uncertainty is important, because it shows that even after centuries of studying stars, we still encounter phenomena that stretch our understanding. The stars around us are not breaking the laws of physics. They are revealing where our models are incomplete. Betelgeuse showed us violent mass ejections. Tabby's star showed us chaotic dimming from debris. Young stars revealed unstable planetary systems. Red dwarfs revealed extreme flare activity. Our sun reminded us it can disrupt our entire technological civilization. And Przybylski's star reminds us that stellar chemistry still holds mysteries. This is not a cosmic extinction wave. It is a shift in perspective. For most of human history, stars were steady points of light. Now we know they are turbulent, unstable, and alive with motion. The night sky looks calm. It isn't. Behind that calm surface, nuclear fusion, magnetic storms, and plasma eruptions are happening constantly. Some anomalies are simply the natural complexity of stellar evolution. Others are puzzles waiting for better data. The universe is not becoming more dangerous. We are becoming more observant. And that changes how we search for life, how we evaluate habitable planets, how we understand our own sun. The stars around us are not failing. They are revealing that the cosmos is more dynamic, more volatile, and more intricate than we imagined. And for the first time in history, we are watching closely enough to see it.